So in this lecture, we continue our comparison for the various modes of convergence that we have defined, and we want to explore their interdependence or interrelationship between these modes of convergence. So we recall that we stated this lemma and we proved some parts of this lemma. So the first one was that uniform convergence implies L infinity convergence. So we already have seen this. This is actually quite trivial. We have also seen that L infinity convergence implies all convergence. This is also something we have proved in our last lecture. And we have seen that L1 convergence implies convergence in measure. So we have already proved this part. So in this lecture, first of all, we will prove this part and this part, third and fifth, where almost uniform convergence implies both pointwise convergence almost everywhere as well as convergence in measure. So the third part is convergence pointwise almost everywhere, and the fifth part is convergence in measure. So let's look at the proof for these parts. So we want to show that Fn converges to F almost uniformly implies Fn converges to F pointwise almost everywhere. So let's start with the definition of almost uniform convergence, which is that given epsilon greater than 0, there exists a measurable set E epsilon such that the measure of E epsilon is less than or equal to epsilon, and Fn converges to F uniformly outside of E epsilon. So this is the definition of almost uniform convergence. So given this definition, we can find for each n greater than or equal to 1, we can find a set En, a measurable set En, such that the measure of En is less than or equal to 1 over n, and Fn converges to F. So let me write here m rather than n, because I am using n for the sequence Fn, Em and E1 over m here. So Fn converges to F uniformly outside Em. So for each m, we have found a measurable set Em which has measure less than or equal to 1 over m, and Fn converges to F uniformly outside of Em. So now we can take E to be the intersection of all these Ems. So this means that the measure of E is less than or equal to the measure of Em for each m, and this is less than or equal to 1 over m, and since m can be taken as large as possible, this implies that the measure of E is equal to 0. Now let's see what happens on a point x which belongs to the complement of E. So the complement of E is nothing but the union m greater than or equal to 1 of the complements of Em by definition. This means that x belongs to Em naught complement for some m naught in n. So it belongs to the complement of one of these Ems, and so this implies by the construction of our Ems that the modulus, so given given epsilon greater than 0, there exists a capital N belonging to N such that modulus of fnx minus fx is less than or equal to epsilon for all n greater than or equal to n for this particular x that we have chosen here, because it belongs to em naught complement. So this n here will depend on your m naught. So this means that fn converges to f pointwise on E complement, and because the measure of E is 0, this means that fn converges to f pointwise almost everywhere. So this shows that almost uniform convergence implies convergence pointwise almost everywhere. Now we come to the fifth part, which is that we have to show that fn converges to f almost uniformly implies that fn converges to f in measure. So given epsilon greater than 0, let me again repeat the definition of almost uniform convergence. There exists a set E epsilon in B, in the sigma algebra B, such that the measure of E epsilon is less than or equal to epsilon, and fn converges to f uniformly outside E epsilon, outside that set E epsilon. So this means that on E epsilon complement. So this means if we write this, if we unpack this part, fn converges to f uniformly outside E epsilon. So what does it mean? This means that given eta now greater than 0, this is another arbitrary positive number, there exists a capital N such that the modulus of fnx minus fx is less than or equal to eta for all n greater than or equal to n and for all x in E epsilon complement. So I just written down what it means for fn to converge uniformly to f on E epsilon complement. So this is the statement that given any eta now greater than 0, there exists a capital N such that the difference fnx minus fx is less than or equal to eta for all n greater than or equal to n and for all x in E epsilon complement. So this n here, remark that this n depends on, first of all it depends on epsilon, because this uniform convergence is outside E epsilon, which in turn depends on epsilon. So it depends on epsilon. It also depends on eta, but it does not depend on x in E epsilon complement. So this means that this capital N, this threshold capital N, works for any x in E epsilon complement. Okay, so now we have this. So this implies that the set of points in X such that the modulus of fnx minus fx greater than or equal to eta is therefore a subset of E epsilon for all n greater than or equal to this capital N, because outside E epsilon it must be less than or equal to eta, right? For all n greater than or equal to capital N. So this is the kind of set that we want to estimate when we are talking about convergence in measure. So therefore the measure of this set is bounded above by the measure of E epsilon. So this implies that the measure of this set of points such that fnx minus fx is greater than or equal to eta is less than or equal to the measure of E epsilon, which is less than or equal to epsilon. This is for all n greater than or equal to capital N. This means that the limit of this sequence of terms, if I call it an, then the limit of an as n goes to infinity is 0, because since modulus of an, which is the same as an because it's positive, this is less than or equal to epsilon for all n greater than or equal to capital N. So here in the sequence an, this eta is fixed, and so we have proved that fn converges to f in measure. So this completes our proof for the easy implications 1 to 5 for all these implications. So it's actually quite useful to have a picture in mind. So this is a map of implications of the various modes of convergence we have seen. So there are 7 in total. We have pointwise almost everywhere. Then we have uniform, almost uniform, measure, L infinity norm, and convergence in L1 norm. So uniform implies pointwise is quite basic, and so is pointwise implies pointwise almost everywhere. So this part and this part is trivial. Now uniform implies L infinity norm. This was part 1 of our lemma. Then L infinity norm implies almost uniform convergence. This was part 2 of our lemma. Then part 3 was almost uniform implies pointwise almost everywhere convergence. Part 4 was L1 implies measure convergence, and part 5 was almost uniform implies measure. So of course, if uniform implies L infinity and L infinity implies almost uniform, then this is also taken care of. So we have this set of implications. Now we will go back to our escapes to infinity and see that we are not able to invert most of these implications. So let's see the escape to horizontal infinity example that we had. So this was the sequence of indicator functions for the interval n plus 1, and we showed that fn converges to 0 pointwise and also pointwise almost everywhere, but let us show that fn does not converge to 0 in measure, and so this would imply that Fn does not converge to 0 almost uniformly in L1 norm, uniformly in L infinity norm as well, because the measure convergence is implied by almost uniform L infinity as well as L1. So if it does not converge in measure, then it does not converge in any of these 4 modes. So let's see why it does not converge to 0 in measure. This is simply because the measure of those points x in R such that the modulus of Fnx is greater than or equal to epsilon. For example, I can choose epsilon strictly between 0 and 1. For example, epsilon can be taken to be half, and then the modulus of Fnx greater than or equal to epsilon, the measure of such sets is precisely equal to 1 for each n. Therefore, it cannot go to 0, and so Fn does not converge to 0 in measure. So this is an example which shows that convergence pointwise almost everywhere does not imply almost uniform convergence, and so we do not have this reverse implication. Now let us look at escape to width infinity again, which was the sequence of functions defined by 1 over n indicator function of the interval 0 to n. So we had seen that Fn converges to 0 uniformly, and this implies that Fn converges to 0 pointwise almost everywhere, and then it also implies almost uniform convergence. It also implies L infinity convergence, and it also implies convergence in measure, but Fn does not converge to 0 in L1 norm, because the L1 norm is fixed at the value 1. This is for all n. So we see that measure convergence in general does not imply L1 convergence. So in fact this implication also does not hold for our escape to width infinity example. Another interesting example was given by escape to vertical infinity, where we had the sequence of functions Fn given by n times the indicator function of the interval 1 over n to 2 over n. So we have seen that Fn converges to 0 pointwise, and so pointwise almost everywhere, but it does not converge uniformly to 0. Now we claim that in fact Fn converges to 0 almost uniformly and hence also in measure. So let's see why this is true. So let given epsilon greater than 0, let E epsilon be the set with the interval 0 to epsilon, and now if we choose n, capital N, such that 1 over n is less than or equal to epsilon, then the modulus of Fnx is actually going to be 0 for all n greater than or equal to n and x belonging to the complement of this interval 0 epsilon. So what is happening here? So we had these intervals 1 over n to 2 over n, and we have some threshold epsilon. Let's say this is epsilon. So if n is large enough, so for example if we take 1 over capital N, 2 over capital N, so actually I should here take 2 over capital N, so that the entire interval is between 0 and epsilon. So then this interval 1 over n to 2 over n becomes inside E epsilon, and so because fn x is n times the indicator function of 1 over n, 2 over n, then for any x outside this interval, so any x here in this region, so for example x could be here, then the indicator function gives you the value 0, because your interval 1 over capital N, 2 over capital N is inside E epsilon. So this part is E epsilon. So outside E epsilon you are going to get 0, and this happens for all n large enough. So we see that this is almost uniform convergence, where our exceptional set it can be chosen to be the interval 0 to epsilon, and so it also converges to 0 in measure, because almost uniform convergence implies measure convergence. But fn does not converge to 0 in L infinity norm or in L1 norm. The L infinity norm for each fn is actually 1, and so is the L1 norm for each fn. So I leave it to you as an exercise to check that both these equalities are true. So we have seen that in this case fn converges pointwise to 0, pointwise almost everywhere to 0, almost uniformly and in measure, but not in any other way. So if we go back to our map, so here this part, this implication does not hold. Of course also this implication does not hold, and also this implication does not hold. The final example is the typewriter sequence, which we saw that the sequence was taken to be the indicator functions of the interval n minus 2 to the power k over 2 to the power k to n minus 2 to the power k plus 1 over 2 to the power k, whenever n lies between 2 to the power k and 2 to the power k plus 1 for some k which can be either a natural number or 0. So this is the typewriter sequence that marches back and forth on the interval 0, 1, and fn we have seen that does not converge to 0 pointwise almost everywhere, but fn converges to 0 in L1 norm. So because fn converges to 0 in L1 norm, this implies that fn converges to 0 in measure as well, and because fn does not converge to 0 pointwise almost everywhere, this implies that fn does not converge to 0 almost uniformly, pointwise, uniformly, or in L infinity norm. So it violates all other modes of convergence except L1 and measure. So if we go back to the implication map, so we see that even this one does not hold in general, and of course we have seen that pointwise almost everywhere does not imply pointwise, and similarly uniform convergence almost everywhere or in L infinity norm does not imply uniform in general. This is because just as we did for pointwise almost everywhere does not imply pointwise, we can change the sequence on a set of measures 0 so that it violates uniform convergence or pointwise convergence. So we have given examples where none of these or all of these implications fail to be inverted. Now what I can say for final few words for this map is that we have seen though that convergence in L1 norm implies that there is a subsequence which converges pointwise almost everywhere. So this is extracting a subsequence, and in fact one can strengthen this a little bit, and even for measure there is a subsequence which converges pointwise almost everywhere. So I'll just state this as a lemma and leave it to you as an exercise, that if Fn converges to F in measure, then there exists a subsequence Fnj such that Fnj converges to F pointwise almost everywhere. So I leave this proof as an exercise. So just try to mimic the proof for the case when we had L1 convergence and we extracted a subsequence by taking a fast enough subsequence, and then that subsequence converges pointwise almost everywhere, and a similar argument works for this case also.